in the upper Faria catchment. We have many criteria to select the preferred site. First is the infiltration capacity and storage. Second is type of the aquifers. We have confined and unconfined aquifers. And we have also the degree of fracturing in the formations and the slope and the land use. To go directly to the preferred location of the artificial recharge, we develop a method called weighted index overlay analysis. This is a simple and straightforward method for a combined analysis for multi-class maps. And this method use the maps for the previous mentioned criteria, and to apply this method by giving a value for a raster map method, value for rasters, and this value can be given according to the human judgment and can cooperate in the analysis. This weight represents the relative importance of parameter vis-a-vis the objective of the, which is artificial recharge. WIOA methods take in consideration that the relative importance of the parameters and the classes belonging to each parameter. So we make the maps and use the GIS raster techniques. The maps for the criteria to select the best sites for the artificial recharge scheme shown in we have 4 criteria, and the results we get the final one in the left, which is show clearly the preferred location in the for artificial recharge along the catchment. This map shows that the most favorable area located in the western part and the underlying rocks along the main wadi. Now we are going to study the optimum artificial recharge method. We will present the available artificial method and decide which is the suitable one, the more suitable one. First, we start with well injection method. This method is not feasible because of the poor quality of the floods and the base flow in the wadi, which includes sediments, loading, and wastewater, and this will put the groundwater at risk, so it will not be visible. Second method is induction method, and this is also not visible because this depends on presence of continuous supply of flood, and this is not available in the area, so it will not be visible. Third method is spreading basin method, and this is also not favorable and not visible because there is a presence of hard limestone rock in the Eocene area in the western part of the catchments, and this is hard rock, and intensive use of the also in the lower area there is intensive use of landfill, so it will not be visible to make spreading basin in this alluvial flat area. So finally we go to that the optimum artificial recharge method shall be make a retarding for the flood by retention structure like a dam or terrace in the area covered by Eocene formation and the alluvia. Final decision was taken to construct retention dam in the upper Wadi Faria subcatchment and not to build retention in the other branch, Wadi Badan, because the result of continuous presence of wastewater in Wadi Badan. So we are working now in the last branch of Faria catchment, which is sub-catchment Faria. This picture show exactly the location of the retention dam and according to the main wadis of the two branches. After decide the location of the dam, we make assessment for the infiltration and storage capacity in the upper Faria catchments, or exactly in the location that will be used to construct the dam. In general, favorable geological formation to receive recharge water are Cretaceous, Bet Kahel and Bet Lahem and Jerusalem formation, and the Eocene Gene formation and Quaternary alluvial. These rocks are naturally fractured and crustifications in some places and relatively deep groundwater levels, which is good from point of view of storage. Also, the favorable geological formation are being located in more upstream part as well as in the lower parts of the upper Faria catchment. Now we are going to the design parameter and engineering design for the dam. We need some information to start design for this dam. We want the rainfall data, which are available in the nearby stations. Also, we need runoff data from nearby flume in the downstream of the wadis at Al-Badan and Faria subcatchments. From these rainfall and runoff data, we can generate the runoff coefficients, and these runoff coefficients will be used to calculate exactly the runoff volume for typical storm event to be anticipated at the dam site. A 2 years return period for flood events has been considered to compute the required storage capacity, and it was about 34,000 meter cube that can be retarded behind this dam. The dam is already implemented in 2013, and the picture shows exactly this dam based on the storage capacity. We came up to the value, the height crest spillway about 2.6 meter the high, and we have width spillway about 5 meter. We have also release pipe had been installed at the bottom of the dam body to release poor quality wastewater from upper parts of the wadi. This is pipes definitely not to make any recharge in the downstream. It's just to release the wastewater from the upper parts. Also, because the area is prone to earthquakes, so several dam break scenario were simulated using dam breaks model. The results was that in case instantaneous break of the dam, expected maximum water depth is about 2.5 to 3 meter in narrow uninhabited valley. It is clear in the pictures. And also about half to 1 meter in the agricultural area of Bet Hassan to downstream, and this could be accepted. Relevant parties in the artificial recharge projects. We have UNESCO IHE supporting related research in cooperation with the Najah University and following up also the construction works from distance. PWA, Palestinian Water Authority, monitoring the advance of the construction works. The construction works, as we mentioned, it was commenced on autumn 2013 and handed over by the end of November 2013. The picture shows the progress of the works in the dam. Now we go to the effect monitoring of the dam. The requirements to make or the activities required to monitor we have to continue collection the rainfall and the dam reservoir level and related flood volumes. Unfortunately, there was the monitoring just made for 1 year, one rainy season, because there was leakage below the dam, and this is we need at least 2 rainy seasons to exactly monitor the effects of this dam. Also, we have damage for the perforated pipes, which was used to collect the wastewater from upper part of the dam, and this may cause mixing of the wastewater with the retarded water behind the dam. And also we need monitor groundwater level. We have one well groundwater. It is away about 500 meters, and this can be used to monitor the effects of the artificial recharge, but it needs diver to be installed at the rising main to the well. Also, we have to determine the sediments load in the reservoir upstream to assess the artificial recharge, and sometimes we need to remove these sediments. Our recommendation after this representation is to rectify the leakage below the dam and to replace perforated pipes system by a bypass trapping the wastewater some about 250 meters upstream of the dam to avoid any mixing wastewater with flood water, and also to observe the installed diver of the reservoir level and to install diver to measure groundwater level at the mentioned well. Anticipated to receive exactly the effects of the dam of this project to be about in the next rainy season 2017 and 2018. Thank you very much.
Thank you very much, Mr. Saleh. Our next presenter is Ms. Randa Tuffaha. She is currently the director of the Laboratory Directorate in the Water Authority of Jordan, and she holds a bachelor degree in chemical engineering from the University of Alexandria. She's been working on water quality issues for more than 25 years, and she has been engaged in implementing analytical techniques for monitoring the chemical constituents, notably organic compounds in water, and applying quality assurance, quality standard. And she's played a major role in assuring the accreditation of her laboratory by the UK Accreditation Committee and by the IAEA. She's worked a lot on different projects, and she's been a technical assessor with the Jordanian accreditation system since 2004 and participated in many scientific research on water quality at national and international level. Member of different scientific and technical committees in the field of water quality. I welcome Ms. Tuffaha to give us her presentation.
بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. This is the outline of my presentation. We will introduce the research project and the aims of the project, methodology, results and discussion, and recommendation. Due to the stop of using unleaded benzene in Jordan, we have to search for suitable boosting oxygenates to raise the octane number in benzene. Therefore, the best choice was methyl tertiary butyl ether. As there is no any baseline data regarding these compounds, we have to initiate that time research projects which has been approved and funded by Ministry of Higher Education Support Research Fund. These projects last for 2 years, And the aim of project was to investigate possible occurrence, distribution, and sources of MTBE and other gasoline components, BTEX compounds. I would like to highlight a little bit about the MTBE compounds, that it is relatively highly soluble in water. Also, it is low soil absorption and is slowly biodegradable. And it had the potential for persistent contamination of groundwater in case of release to environment through spills or leaking from storage tanks. Also, the BTEX includes several compounds, including benzene, toluene, ethyl benzene, and xylenes isomers. Regarding methodology, we choose the study area in Amman-Zarqa Basin and Yarmouk Basin. This area is vital area, and more than 50% of population lives in that area, in addition to other industrial and agricultural activities. Also, in Amman-Zarqa Basin, it is considered one of Jordan's biggest groundwater basins, and the domestic water supply is based entirely on groundwater. This is the geology and the structure of the study area. You can observe here that we have different aquifers, but the main aquifers is P2A7, which is unconfined aquifer and subjected to contamination. According to our study, we have in the study area 3 types of aquifer. The upper aquifer, it is BT07, and the middle aquifers, it is A4 and A12 formations, and the lower aquifer is Kornob aquifer. According to vulnerability of the study area, it was noticed that the area is within low to moderate class subjected to contamination. Actually, here this map shows the distribution of gas stations in the study area. We have here many, around 276 gas stations. All tanks are owned by Jordan Petroleum Refinery and the private sector, and they are of single-walled, and the ages of these tanks ranged between 1 to 40 years for tanks owned by GBR, and the age of other tanks by private sectors are from 1 to 13 years. Also, the site selection, we choose site selections for wells and springs located in the study area within less than 1 kilometer approximately from gas stations. Another thing, we choose that wells in that area because there is a presence of car services stations around inside Protection Zone 2 for water resources, in addition to geological characteristics for wells and springs locations, which is mainly distributed and direct connecting to aquifer, especially in Zarqa River watershed. Here we can see that most of sampling location of wells were distributed in the 3 aquifer types, most of them located in the upper aquifer B2A7, which is considered a vital basin to supply water and vulnerable to pollution. Other sampling locations, wells located in middle and lower aquifers. Here the map shows the sampling sites which were chosen around 1 kilometer from gas stations, and most of them were located in the upper aquifer. In addition to that, to ensure the results of analysis, we chose also another groundwater samples that is not subjected to be polluted by MTBE or other petroleum derivatives. Sampling campaign, actually we arranged sampling to the sampling sites in winter